All right, in this final video about estimation, we're going to talk about comparing two different populations. And this has a lot of application to many different things. It could be before and after natural disasters like housing costs and stuff like that. It could be even used in schools like grade averages based on teaching methods. It could be there's lots of different things if you have two different samples that you want to compare. So that's what this one's going to go about. All right, same idea as in the previous videos. If you know sigma or don't know sigma, that's going to make a difference on what formula you use. And I do want to point out to you that the formulas are in here. So here's our error formula. Ooh, that's a very bad box. Here, let's try that again. That's our error formula, and then here's how we would actually create our confidence interval. And this is sigma squared, so sigma of population 1 squared and sigma of population 2 squared. And then our ZCs are found by doing the same thing, and we just have two different things. So just pay attention to this box, and this will help you see where all those numbers and stuff are coming from. So let's do an example with this. I'm going to make this fit a little bit nicer. All right, the U.S. Geological Survey compiled historical data about Old Faithful geyser from 1870 to 1987. Let x1 be a random variable that represents the time interval in minutes between Old Faithful eruptions for the years 1948 to 1952. Based on 9,340 observations, the sample mean interval was, for this first sample, 63.3 minutes. Let x2 be a random variable that represents the time interval in minutes between Old Faithful eruptions for the year 1983 to 1987. Based on 25,111 observations, the sample mean time interval was 72.1 minutes. Historical data suggests that we have these two population standard deviations. So let mu1 be the population mean for x1 and let mu2 be the population mean of x2. Compute a 99% confidence interval for mu1 minus mu2. All right. If you recall, these formulas right here, keep those handy. You will want those. So we need to use that formula to find our intervals for this one. Okay. So our margin of error formula for this one is going to be ZC. We've got sigma 1 squared over n1 plus sigma 2 squared over n2 and the square root of that. So we have that information and we can plug in these values. Now we find the ZC by looking at that same table we looked at earlier. I'm not going to continually pull that up again. So the ZC for 99%, which is what I want, is 2.58. I'm going to have 2.58. Okay, sigma 1 is 9.17 squared over n1. If we recall, that's kind of up here where it talks about based on 9,340 observations. That is our n1. So 9,340. Plus sigma 2 is 12.67 squared, and this one has quite a few more observations. It has 25,111 observations. So, and this is the calculation that we'll now have to do. And we get 0.32. All right, then to actually find our interval, it is mean 1 minus mean 2 minus our E. It's going to be mu1 minus mu2 in the middle. And then we have mean 1 minus mean 2 again, plus our E. Well, we found mean 1 is up here, and mean 2 is right here. All All right, so I'm just going to type these specific ones just to help out. All right, so we've got 63.3 minus 72.1, and then minus our error, which we didn't get to be very big. It was 0.32. And then that's going to be that first one. And then over here, we'll have the same thing, except for plus. So 63.3 minus 72.1 plus our 0.32. All right, so our values that we get for that, we would get negative 9.12 and negative 8.48. And each of those are minutes. So negative minutes. Okay, well, let's see what that part B is going to have us talk about this a little bit. All right, so comment on the meaning of the confidence interval in the context of this problem. Does the interval consist of positive numbers only, negative numbers only, a mix of positive and negative numbers? Does it appear at the 99% confidence level that a change in the interval length between eruptions has occurred? Many geological experts believe that the distribution of eruption times of Old Faithful changed after the major earthquake that occurred in 1959. So the fact that these are both negative actually is significant because what we're saying is every time we take the sample mean from the population mean from the first population and subtract out the population mean from the second one, we're always going to get a negative. That means that this mean 2 would always be bigger. That would mean it was always bigger. So these consist of only negative numbers, and that the second population, so our second population, let's even be more specific. So after 1952, because really it just did the from 1983 to 1987, but so that the time between eruptions was lengthened since 1952. So scientists are probably right that that major earthquake that occurred in 1959 did have a major impact on it. I mean, it has lengthened it by what I would say almost between 8 and 9 minutes. That's kind of a big deal there. So yeah, it does make a difference. If they're all positive, all negative, they're all positive, what that means is our first population is typically bigger. If they're both positive and negative, that means they take, like, sometimes one's bigger, sometimes the other. So there really is no difference between the two. But the fact that they're both negative here means our second population numbers are bigger. All right, so how does this change when we don't know our sigmas? Well, not much changes. Instead of using Z's, we use T's, which we talked about that in our last one. So if you notice, the formulas look pretty much exactly the same, except for we're going to use a TC. So I'm not going to necessarily do a full-on example with that. I'll make sure I leave that in the notes for those of you that want to add it to your class notes. But for the sake of this video, if you're only watching the video, you won't see those. So I'm going to kind of skip over this one. All right, so once again, how do we figure out which one we're going to use? Do we know sigma or do we not? We're not really going to pay attention to this one over here for what we're doing. So just, do I know sigma or do I not? I will point out our degree of freedom, because we have two different populations. We pick the smaller of the two. So if I have a population that is 10 and I have a population that is 22, my degrees of freedom would be 9 and 21. Well, I would pick the smaller one, so I would have a degree of freedom of 9. So all that does is allows, I guess, more room for error there. All right, what happens if I need to mess with proportions? Well, same idea, except for now I've got two sets of proportions, and the hardest part for a lot of people is keeping the numbers straight. And so just kind of watch out for that. But here's our formula for it. We're still using our ZC, and we're still going through all that stuff. And here's a quick way to interpret the confidence intervals for either one. So if they're only negative, this is what I was talking about. If they're only negative, that second population is usually bigger, or the second proportion, second mean, whichever one. If they're all positive, then that first one has a higher average or proportion. And then if they're both, you can't really tell which one is bigger. Let's do an example with the proportions. Just so we have that. Okay. Isabel Myers was a pioneer in the study of personality types. She identified 4 basic personality preferences that are described at length in a book, A Guide to the Development and Use of the Myers-Briggs Type Indicator by Myers and Macaulay. Marriage counselors know that couples who have none of the 4 preferences in common may have a stormy marriage. Myers took a random sample of 375 married couples and found that 289 had 2 or more personality preferences in common. In another random sample of 571 married couples, it was found that only 23 had no preferences in common. Let P1 be the population proportion of married couples who have 2 or more personality preferences in common, and let P2 be the population proportion of all married couples who have no personality traits in common. So we're going to find a 99% confidence interval for P1 and for P1 minus P2. So once again, the things that we're going to need to be able to find, we need the ZC for our 99% confidence, and that is 2.58. We also need our N1 and our R1. So our N1 is 375 married couples, and they said 289 have 2 or more in common. Then we also need, which will help us find our P1, PCAP1. All right, so we need our N2 and our R2. So our N2 is 571, and our R2, our successes there, would be only 23. Okay. And we're going to use those to find PCAP1 and PCAP2. And we could just leave them as a fraction. So we could say 289 out of 375. Or you could go to a decimal and estimate them. Either way is acceptable. This one estimated is 0.771. Likewise, this one could be 23 over 571. Or estimated would be 0.04. So much lower probability there for proportion. All right, and then we're going to go through and use our actual formula to set up to find that margin of error. And we will be using the ZC, the PCAP1, the PCAP2, as well as the N1 and N2. So refer back to that formula to see what numbers go where. And then I'm going to go ahead and set this up, and you will kind of see. I'll give it a moment here. All right, so this is our formula that we would get set up with all of our numbers typed in. And then you would actually go through and type all that in to figure out that. And our margin of error here would be 0.06. And then we would actually need to figure out what our confidence interval would be. So we do minus our E. And PCAP1 minus PCAP2. Ooh, that's terrible. Plus our E. We'd actually do those calculations and figure out what this proportion would equal. And the first half of this interval is going to be 0.671, and the last half is going to be 0.791. Okay, and that's our interval. So explain the meaning of the confidence interval in part A in the context of the problem. Does the confidence interval contain all positive, all negative, both positive and negative? What does this tell you at the 99% confidence level about the proportion of married couples with two or more personality preferences in common compared with the proportion of married couples sharing no personality preferences in common? Well, we can definitely say that they are all positive. And remember, proportion 1 represented two or more personality preferences in common, and P2 represented no personality preferences in common. So when I did two or more preferences in common minus no personality preferences in common, we got that interval from above. So there is a much higher proportion of couples that have two or more couple of married couples, because that's what they were studying, that have two or more personality preferences in common. In fact, it was between 67% to 79% more couples that have that many in common. So this is a quick rundown of all of the differences as well. So good luck with all of the estimation problems that you are doing.